Okay, so we're going to look at some other types of graphs today. The first one that we're going to look at is called an exponential. So an exponential graph has x as an index. So rather than having x to the power of, you have something to the power of x. So we're going to look at a really simple one. Y is equal to the power of x. And we're going to do up a bit of a table of values so you can start to see what it is that's happening and hopefully make some predictions about the graph from there. So pick some values for x and then we'll calculate the y's. So I'm going to start off just at -4, -3, and then we're going to work out what y is. So if x is -4, remember the negative turns it into a fraction, so it's going to be 1 over, and then 2 to the power of 4, so 2 to the power of 4 is 16. So this is equal to 1/16, which is a fairly small number when it comes to graphing. What about when x is -3? So again, 1 over and 2 to the power of 3 is going to be 8. So every time we reduce that power, we're reducing the number of 2's that we're multiplying by. So now this one's going to be equal to 1/4. -1, well, that's going to be equal to 1/2. 2 to the power of 0, remember anything to the power of 0 is equal to 1. 2 to the power of 1 gives me 2, 4. So now we're just multiplying by 2 for each step. So have a look at the numbers. We start off with something that's relatively small. 1/16 is a fairly small number. And then even though the first few steps are still all less than 1, the difference between them is increasing a little bit each time. At first we go up by 1/8, and then we go up by 1/4, and then we go up by 1/2. And then look what happens to the change. Once we get to 1, we go up by 1, we go up by 2, we go up by 4, we go up by 8, then we go up by 16. So this is an increasing function, but the rate that it's increasing is increasing as well. So what does that mean for the graph? Well, I'm going to switch to GeoGebra so that we can have a look at it accurately, because as you've seen in the past videos, my sketching skills are not the greatest. So if I wanted to graph that one that I just did, it looks like this. So you can see when we had the -4, 1/16, we're talking about something quite small. But then it starts getting bigger. But not only is it getting bigger, the rate that it's getting larger is increasing. So the graph starts to get more and more steep as time goes on. Now you can see the change from 3 to 4 is quite significant. If we move this graph, you can see what's happening is it's getting steeper and steeper as x gets bigger. By the time we've hit x equals 5, this graph is extremely steep. This is what's called exponential growth. And this is why things like when they talk about compound interest, or if they talk about the growth in bacteria, this is why it's so important, because at first it's slow and it's small and it's manageable, but very quickly it's gotten very large. And that's when, if you're talking about bacteria, things spiral out of control. If you're talking about money, well, that's when you start to earn bucks. So what happens if I change the constant? So that was 2 to the power of x. What happens if I change the constant? Well, let's turn that one off. 5 to the power of x. Well, what does that look like compared to the one you just saw? Well, any similarities? They both cross at this point here, don't they? They both cross at 1. So 5 to the power of x is steeper. That's that one there. You can see it's just come up in bold. 5 to the power of x is steeper. So at first it's smaller, which makes sense. Like if you're multiplying 5's together, you get a larger number than if you're multiplying 2's together. So if we then put it on the bottom of a fraction, you're splitting it up into many more pieces. So it starts off smaller, but its rate of growth is much faster than 2 to the power of x. So these are exponential graphs. Exponential graphs are really quite easy to draw because they share some characteristics. they can never cross the x-axis. There is no value that I can put in there to make y equal to 0. There is no number I can put in for x to get 2 to the power of something equal to 0. So the x-axis is an asymptote. The graph approaches it but never crosses it. And whatever value we have as our base number, 2, 3, 5, 9, 1,000, whatever number that is, if I substitute in x is equal to 0, I always get 1. So your exponential graphs always cross at 1. Once you know the shape and where it crosses and where it approaches, drawing the rest of the graph is really quite simple. So a logarithmic function is something slightly different. And you may have noticed on your calculator you have a log and an ln button. And if you've never used them before, now is your chance. How excited are you? I can tell you're just busting to finally give this a go. So pick some numbers for x. Again, you're going to substitute them in. Try some negatives first. And then you've got this one here, ln, which is called a natural log. And this has a base e, which you can see is written above there. So today we're working with ln. So you've got your table. You're just going to press ln. And then we've done -3 equals math error. So that's telling you that there is no value for that. You'll get the same whenever you type in a negative. Okay, but once we go past x is equal to 0, so if we start doing the log of 1, then we start getting answers. So log of 1 is equal to 0. So I want you to do your table of values. I want you to pause the recording here and substitute these in and see what you get. And then once you've got some values written down, or if you've got some questions that you're hoping are going to be answered, start the recording up again and we'll see what you get. So the first couple that you try, when you've got the negatives, your calculator should come back telling you math error, math error. There's a problem. You can't take the log of a negative number. But once you start putting in some positive values, you get some answers. So what that means for a graph is that there is no graph when x is negative. So we're only on the positive side, and x is equal to 0 is our asymptote. It's a smooth curve. It goes through the point 1 and it tapers off. So we can look at other base. So this is also log x on here now. So that's that dark one there that you can see, log x. So again, it's related to the exponential in that idea that the shape is always similar. It always crosses at 1. It's just how steep. That's what changes. Now later on you'll learn that the exponential and the logs are related and how one relates to the other. But once you know the shape, you know it crosses at 1, it's a very easy graph to sketch. Now I'm going to stay in GeoGebra because I want to show you the graphs of some cubics. So the cubic, you'll have seen my very poor attempt at drawing a cubic earlier. Looks like this. So that's a cubic function. So this is y is equal to x cubed. Again, if you do your table of values, it'll show you what's going on there. When x is equal to 1, y is equal to 1. When x is equal to -1, y is equal to -1. X is 0, y is 0. And then after that, the rate of change increases. And it has point symmetry around the origin. So the top half of the graph is reflected in the bottom half of the graph, but it's spun around, not just flipped over the axis. What is going to happen to that graph if I change it instead of x cubed? I change it to x cubed plus 2. Well, what I get is exactly the same graph, just moved up 2 units. So if I subtract 2, I'll get exactly the same graph moved down 2 units. So the constant, again, just like in a straight line, the constant tells you the intercept. Plus you move up, minus you move down. Everything else is the same. What if I move the plus 2 inside the brackets? So if I move the x plus 2 inside the brackets, well, in this case, it moves sideways. Exactly the same graph, just shuffled to the left. If I had x minus 2, it would shuffle to the right. So once you know the basic cubic shape, figure out your intercepts. So in the case of x plus 2 all cubed, it's minus 2, you know the shape. Follow the rest of your graph. So we're going to spend quite a bit of time working through 5.9. You need to be really familiar with the basic shape of these graphs, how to find intercepts, whether you should be moving up and down or left and right. So I would like you to do a lot of practice. Please don't skim through this and only do every 4th or 5th question. You've got to be able to do this fast and efficient. Otherwise, you will waste way too much time during your exams. Good luck, and I'll see you in class.